In this module, we will consider the superposition of waves. A fundamental property of linear waves is that we can add together any solutions of the same linear wave equation. If two waves are traveling in the same medium, sound waves in air or transverse waves on a string, anything like this, we will assume that the waves have the same speed, but may be traveling in different directions. If the waves are periodic, then they are allowed to have different frequencies and wavelengths. Superposition always adds the amplitudes of waves that are at the same place at the same time. Key to solving problems with superposition is determining how to express the phase of each wave in terms of the position where you want to determine the value of the superposed waves. Let's consider several examples. The simplest case to consider is that of two waves traveling in the same direction on a string. Both waves share the same x-coordinate values, making superposition easy. The individual waves are given by y1, which is a sine of kx minus omega t, and y2, which is a sine of kx minus omega t plus a phase difference phi. In this example, the two waves are sinusoidal with the same amplitude a and frequency omega. The only difference between them is that they have a phase difference specified by phi. The superposition of these waves is obtained simply by summing y1 and y2. To simplify the expression, we can use the trigonometric identity given below, and with a few simplifications, we find that the superposition is given by 2a cosine of phi over 2 times the sine of kx minus omega t plus phi over 2. Let's consider what the superposition looks like at t equals 0. The amplitude of the superposed wave profile is 2a cosine of phi over 2. This amplitude varies between 0 and 2a, depending on the phase difference phi. In the following animation, the individual waves are represented at t equals 0 with the black lines. The superposition of the two waves is shown in blue. In the animation, the value of phi varies between 0 and 2 pi. The second wave, which includes phi, is drawn as a dashed line. When phi takes on the values of 0 or 2 pi as shown in the illustration, the waves are in phase, the superposition is completely constructive, and the amplitude is 2a. When the phase difference is pi, as currently shown, the waves are out of phase, the superposition is completely destructive, and the amplitude is 0. Now consider sound waves from two speakers connected to the same single-frequency sine wave source. In this case, it is much more complicated to directly express each wave in terms of the same set of coordinates. Instead, let's consider the waves at some point in space a distance d1 or d2 from its respective source. We think of each wave as traveling radially outward from its source and construct the superposition at the single point shown. Using the same identity, we obtain the formula shown for the superposition. The amplitude of the superposition is controlled by the argument to the cosine. When k times the magnitude of d1 minus d2 over 2 is equal to some integer multiple of pi, then the cosine will take on the values of either minus 1 or plus 1, and we get constructive interference. When the argument to the cosine has the value of n plus a half times pi, then the cosine will take on the value of 0, and we have destructive interference. It is useful to think about the superposition in terms of the phase of each wave at the point of interest. Phi1 equal to k d1 minus omega t is the phase of the first wave. Phi2 equal to k d2 minus omega t is the phase of the second wave. And the phase difference is just the magnitude of the difference of the two phases, which is equal to k times the difference in the path length traveled by the two waves. Taking our previous result describing when we obtain constructive or destructive interference, we multiply by 2 and divide by k, and find that when the difference in the path length traveled by the waves is an integer multiple of 2 pi over k, that is, when it's equal to an integer times the wavelength, we have constructive interference. When this path difference is an integer plus a half times the wavelength, then we have destructive interference. For sinusoidal waves, interference between superposing waves can be gauged by the phase difference between waves. When the phase difference is an integer multiple of 2 pi, we have constructive interference. And when it is an integer plus a half times 2 pi, we have destructive interference. If we wish to think about this in terms of path differences, then our phase difference is equal to k times the path difference. And we can then determine via the path difference when we have either constructive interference, when the path difference is an integer multiple of the wavelength, or destructive interference when we have an integer plus a half times the wavelength. If we wish to think about this in terms of a time difference, then our phase difference is the angular frequency omega times the time difference. And we then see that our time difference, when it is equal to an integer multiple of the period of the waves, we obtain constructive interference. And when it is an integer multiple plus a half times the period of the waves, then we obtain destructive interference.